the most mysterious, most predatory, and most mind-boggling objects in the universe: black holes. We've observed them indirectly, we've taken their pictures, we've developed theories. But what if we could touch them? What if we could send a representative to the very edge of this deepest well in the universe? This is no longer just a science fiction fantasy. A group of scientists, led by astrophysicist Cosmo Bambi, is putting on the table what might be the most audacious space mission in human history, sending a tiny probe to a black hole. This isn't just a mission of discovery. It's a challenge that will push the boundaries of physics, subject Einstein's theories to an unprecedented test, and could forever change everything we know about spacetime. So how will we get a paperclip-sized craft to 1/3 the speed of light? And what awaits us at the end of this incredible journey? If you're ready, let's begin. At the heart of this mission, there are no rockets or giant fuel tanks. Instead, there's a technological marvel small enough to fit in the palm of your hand: the nanocraft. Weighing only a few grams and built around a microchip, this tiny spacecraft gets its power from a massive sail. But this sail won't be filled with wind, but with light. Here's the plan. A massive and incredibly powerful laser array, built on Earth, will focus on the nanocraft's ultra-thin light sail. The intense beam of light from the laser, that is the pressure from photons, will push the sail forward. Just like wind pushes a sailboat, but this time the driving force isn't wind, but trillions of photons sent from Earth. The speed this craft will reach with this method is staggering. Approximately 100,000 kilometers per second. That's 1/3 the speed of light. At that velocity, reaching a black hole 20 to 25 light years away would take about 70 years. Once the probe arrives, the data it collects, traveling at the speed of light, would take another 20 years to get back to us. In other words, this is a multi-generational mission, one that its initiators will not see to completion. So why is this journey, which will take nearly a century in total, worth it? The answer is simple: to test the most fundamental laws of the universe. The primary objective: to definitively confirm the physical nature of black holes, specifically to study the famous event horizon. According to the theory of general relativity, the event horizon is a point of no return. But what if it's not? What if, as some alternative theories suggest, it's a solid surface made of exotic matter? As this probe approaches the event horizon, it could measure specific patterns in light, energy, and particle behavior, potentially settling this debate once and for all. The second objective: to test Einstein's theory of general relativity under the most extreme conditions yet. This theory has passed every test thrown at it, from planetary orbits to gravitational waves. But the extreme gravity and space-time curvature near a black hole could reveal deviations or new effects in the theory that we have never seen before. Additionally, invaluable data could be collected, such as directly measuring gravitational redshift and time dilation near the event horizon, studying the accretion flows and magnetic fields around the black hole, and even detecting possible quantum scale effects at the boundary. In short, this mission means going to a laboratory we could never replicate on Earth. Sounds amazing, doesn't it? However, there are two colossal hurdles facing this mission. The first and biggest one: a target. We need to find a nearby black hole. The closest confirmed black hole, Gaia BH1, is more than 1,500 light-years away. That's an unreachable distance for us. However, astrophysicists suspect that smaller, undetected rogue black holes are hiding much closer to us in the Milky Way. By observing the small wobbles in the orbits of nearby stars, or by detecting gravitational lensing effects, we might find a target within a 25 light-year range in the next decade. But without a target, this project remains just a theory. The second major hurdle: technology and cost. We do not yet have a nanocraft that can survive for decades in interstellar space, withstand constant cosmic radiation, and send back meaningful data from such a vast distance. Furthermore, the laser infrastructure needed to accelerate this craft would cost around 1 trillion euros with today's technology. That's a staggering figure. But Bambi and his team are optimistic. They estimate that with advances in energy generation, laser efficiency, and manufacturing, this cost could drop to around 1 billion euros within 20 to 30 years, similar to the budgets of major flagship space missions. This project builds upon existing ideas explored in projects like Breakthrough Starshot, which aims to send similar nanocrafts to Alpha Centauri. But the black hole mission raises the bar much higher, both in terms of distance and the hazardous nature of the destination. So what would a realistic roadmap look like? First, a reachable black hole target must be identified with next-generation telescopes. Then, the nanocraft technology should be tested on shorter journeys, for example, with prototype missions to the outer solar system. The laser system should also be built incrementally, not all at once, perhaps a test flight to a nearby star system, before attempting the black hole mission could prove that the entire system works. And most importantly, the value of this mission isn't tied solely to its completion. Just as the race to the moon spawned countless technologies, every step taken toward this mission will have tremendous spin-off benefits. Laser propulsion could reduce interstellar travel from millennia to decades. The miniaturized space instruments developed would lower the cost of future missions. And the radiation-resistant materials could be used in satellites, space stations, and even industries here on Earth. It's just like the decades-long efforts to detect gravitational waves or capture the first image of a black hole, which made incredible contributions to science and technology along the way. Sending a paperclip-sized probe to a black hole might seem like fiction today, but it's a well-founded concept based on active research. The challenges are massive, yes. This will require generations of patience and dedication, but history shows us that perseverance can make the impossible possible. Even if this mission doesn't launch soon, the pursuit of the idea itself has the potential to revolutionize interstellar travel technologies and deepen our understanding of the cosmos. Perhaps one day that tiny light sail sent by humanity will unlock the door to the universe's darkest secret. We will see together how that future takes shape.